Good afternoon, everyone, and welcome back. Are you able to hear me?
Yes, we can.
Great. Okay, so I'm Kathy Mont. I'm the Deputy Project Scientist for Interstellar Probe, and I'll be introducing our speakers for this afternoon. We will have two speakers in this webinar format, and then we will move to a regular Zoom meeting for the final presentation and for the discussion that will follow. You should have the link in the email you received for the Day 3 connection format. So we look forward to seeing you here and there. Now, our first speaker for the afternoon session is Alice Cocoros, who will speak about the implementation of the Augmented Mission.
Hey there, everyone. Welcome back. Let's go ahead and get started. We can go ahead and go to the next slide. So just as an overview of the technical implementation of the Augmented Mission, Jim has already touched on this in his talk, but in case you missed it, there are very few technical differences from the baseline when it comes to the Augmented Mission. So the payload is similar in mass and power and accommodation. The trajectory is very similar. It's Jupiter gravity assist out of the solar system and into the local interstellar medium, but it includes a flyby of a dwarf planet. The spacecraft is identical with the exception of a few instruments and the software for the GNC system in order to account for the dual axis control. And the heliophysics science operations remains the same for the core instruments while the spacecraft is being operated in spinner mode, which is going to be most of the time. In particular, the focus of this talk, the payload has a few key differences to accommodate the dual axis mode to stay within the maths limit that we've set for ourselves and to perform planetary science and astrophysics observation, which is obviously the most important part. And just as a note on those science operations, to expand upon or generalize rather what Kirby and Mike have talked about in the previous talks, the general course of operation that we're assuming, although it may be possible to perform operations in some cases while the spacecraft is spinning, would be to spin down the spacecraft, establish 3-axis control, execute attitude changes, perform those measurements required to make the planetary and astrophysics observations, and then spin the spacecraft back up. And I also should note that it flybys, in particular because of the large size of data from cameras, might require additional downlink. If you go to the next slide, we'll start this talk like I started my last one, which is to address the instrument menu. So in case you missed my last talk, this is basically an overview of all of the instruments that we thought might be applicable to an interstellar probe, which includes mass and power ranges for each instrument based off of heritage and conversations with the community about current instruments that are in development. And in particular, I wanted to highlight the last 3 categories, which include cameras, which would be the main instrument contributing to planetary and astrophysics observations. So if you go to the next slide, once again, just to reiterate in case some of you missed my talk this morning, we have a mass constraint on the payload of 90 kilograms before contingency and not including spacecraft structures, which would be the particle sweep boom and the ENA boom that allows for those instruments to have the angular coverage that they need. And we have 2 example model payloads. So the baseline was covered this morning and in section 4 of the mission concept report. And today in this talk, I'll address the augmented payload, which is also addressed in Appendix A of the mission concept report. As a reminder, the science traceability matrix is really what drove our choices for these example payloads, but it should be noted that other combinations could be defended, but we needed to pick one. So if you go to the next slide, as I emphasized this morning, and just now, the science traceability matrix is really what's driving our choices. So here I have a summary of the augmented goals in the science traceability matrix. And once again, these measurement objectives result in instruments that drive mission requirements and dictate how those instruments need to be accommodated. So if you go to the next slide, we have an overview of the resources allocated for the augmented payload. So we have a mass of 89.1 kilograms and 90.2 watts required. The percentages of science questions and addressed was calculated by looking through both the heliophysics part of the STM and the augmented part of the STM and addressing which questions were answered by which instruments. So you can see roughly 50% of the measurements are still being performed on particles and fields, which is the main heliophysics measurements you're going to be taking. Then you also have roughly 20% of the science questions being addressed by your imagers, involving flyby imaging and the infrared mapping. And then you also have measurements that address questions both for heliophysics and planetary and astrophysics, including the ENA measurements and dust and neutrals. You can see once again that the payload mass is roughly representative of the per instrument category is roughly representative of how many science questions are being answered by that instrument. So if you go to the next slide, just to highlight the differences between the baseline and the augmented, I wanted to start with the baseline payload again. So here you can see that the instruments that are the same include the magnetometer, the entire charged particle suite, which incorporates 4 instruments, the dust analyzer, the neutral mass spec, as well as the ENA imager. The 2 big differences from the baseline payload in terms of changing what was there involved the plasma waves instrument and the Lyman alpha spectrograph. So these 2 instruments are not included in the augmented payload. If you go to the next slide, instead, what we have is an altered plasma wave instrument that can exist in 3-axis mode, and the Lyman alpha spectrograph was the instrument chosen to be nixed in order to meet the mass cap and include 2 cameras, namely the visible near infrared imager and the visible IR spectral mapper. So looking at the base of the spacecraft here is really the best vantage point to see all the instruments. You can see the particle boom here remains the same, as does the ENA boom on the other side, and as does the MAG and NMS and IDA on the bottom of the spacecraft. But you can see these plasma wave antennas are thicker and much shorter, unfortunately, than the plasma wave wires that were accommodated on the baseline. And you can see the cameras here are right next to the particle boom. So I'll go into these in a little bit more detail. You can see here in terms of the fields instruments, the 50-meter antennas for the plasma waves can't be deployed while the spacecraft is being operated as a dual mode spacecraft. So instead, we have 4 2.5-meter rigid stasers, which are still perpendicular to the spacecraft ram direction and 90 degrees apart from each other to measure the two of the field components. And a sounder is also accommodated to enhance the instrument. It should be noted that one could also consider Voyager-like 10-meter rigid antennas, which would improve the science capability from a Jovian level that the 2.5-meter stasers provides. Lastly, it could also be possible to have 50-meter wire antennas to achieve baseline-like science that deploy from those 2.5-meter stasers after the last 3-axis observation. So once the spacecraft is operating just in spinner mode for the remainder of the mission, but this poses a very high risk. So that decision shouldn't be made lightly. And for just for reference, I still show the magnetometers here which are accommodated in the same way with 2 magnetometers spaced out on a 10-meter boom. Go to the next slide. This is the other really big difference, is that we have 2 cameras on board, which are accommodated near the particle sweep boom. So focusing on the visible near imager first, that enables observations of planetary surface features, distant unresolved planets and TNOs in the cosmic background, as well as sensing of the interstellar medium in the wavelength band, which is nominally 0.4 to 4 micrometers. Pointing accuracy for this would need to be less than 1024 microrads, while the pointing knowledge would need to be less than 471 microrads. Jitter requirements would be less than 50 microrads per second, and ideally the field of view would be somewhere between 2.3 degrees and 5.7 degrees in the cross-track direction for a push room style imager. For the VIR, observations would require 3-axis mode, although, as Kirby mentioned, there may be some ways to accommodate an imager that could still image in spinning mode, which would be certainly something to consider. In terms of the VIS-IR spectral mapper, this is accommodated in order to observe the diffuse redshifted light emitted by the universe beyond the dominant zodiacal cloud foreground that obfuscates such studies when they're performed within our heliosphere. So it has 2 channels that we're considering, a near IR channel and a far IR channel, which are 0.5 to 15 micrometers and 30 to 100 micrometers respectively. And depending on the camera requirements, observations could either be made on a slowly spinning spacecraft or would require the pointing of the 3-axis mode. So for the sake of our study, we've assumed that the observations are made during a 3-axis mode, but it is possible that they could be made otherwise. To keep these instruments, to keep the far IR channel cool, you would need a cryo cooler, and I know there are some questions on that. So at the open discussion session, that's certainly something I'm sure Mike Zemkoff would be happy to address. Pointing accuracy and pointing knowledge are both estimated as less than 1 arcsecond, while jitter requirements would be less than 1 arcsecond per second. The field of view is 1.1 degrees. A far IR channel would have slightly more relaxed pointing accuracy and knowledge and jitter. So the location here on the spacecraft was chosen to limit field of view obstructions, to avoid sun pointing, and also to keep the instruments as cold as possible, i.e. trying to keep them as far away from the RTGs as possible, given the wavelength regime here requiring that the cameras be cold. They're co-bore sighted together, perpendicular to the spacecraft ram direction, because this ended up being the best way to meet all of those requirements. And they're also bore sighted, the bore sight of NMS in particular is 90 degrees away from the bore sight of the cameras, so that NMS can make observations of potential atmospheres of a flyby object, while the cameras are pointed at that flyby object, taking pictures. So if you go to the next slide, the rest of this, just for posterity, covers the rest of the instruments in case you missed my talk this morning, which is to say that we have a particle suite that covers the range of order 1 EV to 1 GeV with full sky angular coverage as needed for the particle instruments. For the dust and neutrals, it's the same as the baseline, once again, pointed to, if you go ahead and forward the slides, sorry. It's pointed to avoid field of view obstructions and optimize for a flyout direction of 45 degrees off the nose. And once again, there's this plane in which the bore sight of NMS is perpendicular to the bore sight of the cameras, so that it can take a look at the atmosphere if there is an atmosphere of the flyby object. And lastly, if you go to the next slide, the ENA imaging is exactly the same as the baseline as well. Add on the boom for angular coverage, and that boom also happens to balance the particle boom on the other side, which is helpful. that's it in terms of the augmented spacecraft.
Okay, great. Thank you, Alice. We have 5 minutes before our next presentation, and I do see one question, which we have the time to cover now, if you're available, Alice.
I am available, although looking at this question, I think that Kirby might be a better person to answer it.
Okay, Kirby, are you available?
I am. I'm sorry. Could you repeat the question, please?
Yes. So we have a question from Tony Freeman. I think you have addressed this already, but if your electro-optical instruments had pointing mirrors, those would probably last through the KBO dwarf planet encounter phase and
Yeah.
give you flexibility to keep spinning on a flyby.
Yeah, that's a great question. Yes, moving parts scare us on such a long mission. There's one more thing to break. That being said, the planetary encounter would happen fairly soon in the mission. So if it broke after that, maybe that's okay. In terms of it's a great question for a mirror to de-rotate. Mirrors, as I understand, they can give you a tangent to the rotation, but they can't truly de-rotate an image. So there are some tricks you can play with, like maybe a despun camera or maybe a scan mirror that helps with part of that for that. But that's something that a future team could take a look at. We opted not to just because of the added complexity, but it's not a bad idea.
Okay, I do not see any other questions. Do we want to take a brief, oh, wait, there is another question, and I think it might be for Kirby as well, maybe.
Chatter on the team in the past has been along the lines of, yes, we would absolutely go out to Planet X if it were there. Of course, heliophysics is paying for this, and so, but I think that's a very, if Planet X, a truly a planet larger than a dwarf planet were really discovered out around the neighborhood of 200 AU, I think there'd be a very compelling reason to go to it with a spacecraft with the capabilities of an interstellar probe. And that would be a conversation for a later time if that large planet actually exists and we find it in time.
Yeah, and to repeat the question, it was from Marshall Eubanks. He wanted to know if Mike Brown found his Planet X out at 200 AU, if we would go to it. So
and if I might interject, we did have one of Mike's graduate students with us at our first workshop for exactly this reason.
And if I could recall one interesting thing from that talk, the graduate student, and I'm blanking on her name, unfortunately, right now, but she said that out there, the hill spheres of the planets are so large that any moons could in turn themselves have moons, and they nicknamed them moons. So it could be a very compelling planetary flyby, if you could even see it that far from the sun.
okay, and
I can briefly comment on the antennas. So from my best of understanding as the payload systems lead rather than the topical field group lead, which would be Stuart Bale. Those long wire antennas really provide the science that you would want to examine in terms of plasma waves. The rigid stasers can only provide a Jovian level, which is really even below that of Voyager. 10-meter antennas that are rigid, like Voyager's, would provide Voyager level science and would certainly provide a lot of insight and addition to what Voyager has done. But as for each topical group lead, you aspire obviously to have an instrument flying that's better than any instrument that's flown before. So really in the trade, we've considered things, I think, even out to 250 meter wire antennas. So then the 50-meter ones start to sound a little more reasonable. I hope that helps address your comment, Tony.
And we are now at the point for our next speaker, but please continue adding questions to the Q&A because we are capturing those all for the discussion that will follow the final presentation today.